Good morning, students. As we are studying segmentation, now we have here a new topic to study, that is segmentation by fitting a model. By fitting, we mean we are here trying to map the data points that best describes your object of interest. From this figure, we get an idea that here we are trying to map all those points that will describe the object clearly. Now we can have edge detections or corner detections and even blob detection. First, we'll try to find out the edges in the given image or corners or blobs, whichever is suitable here. Then we try to form a higher level of compact representation of the features in the image by grouping multiple features according to a simple model. Now here we are trying to fit the feature points, the data points, taking into consideration suitable model here. Now choosing the parametric model to represent a set of features. Now here we will try to look towards some simple models such as lines, circles, or we can even go for a complicated model such as car. By circle, if the input image given to us consists of the object of interest to be extracted from the image has some sort of similarity with the shape, circle shape, then we can apply circle model here. If the image is given in some sense that it has most of the lines or the object here consists of some of the lines that are horizontal, vertical, or something like that, then we can go for application of models as lines. But if you do not have a specific primary shape that you can apply in simple, then we can go for a combination of these primary models that will best suit the shape of the object to be determined in the image. So first you need to do is choose a parametric model to represent a set of features. Once you are done with selecting the appropriate model that will best suit your feature set, then you have to make these feature points vote for the model and find out the membership criteria. You have to check for the membership criteria, whether it is local or not. Here you cannot tell whether a point belongs to a given model just by looking at that point. Here you have to make all of these feature points cast a vote against this model. Okay, now here there are three main questions that arises. What model represents this set of features best? Among the set of models, which model is best applicable? You have to first be very specific to this. Then which of several model instances get which features? And how many model instances are there? After getting some sort of answers to these questions, we can again look for the computational complexity, which is very essential here, as it is infeasible to examine every possible set of parameters and every possible combination of features. We have got some issues with fitting. Here we have a case study as line detection. Now given an image here, you can see if we try to find out the lines, first you need to do is just apply a thresholding over this image in order to get a binary image here. Then you need to apply line detection algorithms or edge detection algorithms. Your lines we want to find is of type horizontal or vertical. So you have to apply, and then you have to look for the edges in the edge map. Now in this case, this particular object covers up the background here, which is having horizontal line. So here you may get some noises in the edge map. The things that are related with these issues are uh, in noise in the measured feature location you have to look for, and again you have to deal with extraneous data such as clutters or outliers, or if there exist multiple lines. Even we have to face the problem of missing data, as some of the objects may occlude some other part of the object in the image scene. Now, if we know which points belongs to the line, how do we find the optimal line parameter? There's a big question here. The answer we can find is with the least square method. We can go for fitting a model using least square mechanism. And in case if you're having outliers, this can be handled with a robust fitting or ransack algorithm. If there exist multiple lines, then we can apply voting method such as half transform or ransack method. And even if you are not sure whether it is a line, then you have to reconsider the model selection here. Now let us see what do we mean by least square line fitting algorithm. Now just imagine that we have a data points given which we have mapped in x and y coordinate system. Looking at this graph, so these are the feature points here. These have been mapped in x and y coordinate system. So each of the point here, now we want to find out a line that will best describe these given data points. So every data point is having two values associated with it, that is x and y coordinate values. We have a line equation here that describes a y-intercept as mx plus b. For each yi, we can and put up into the equation and get mxi plus b, whereas b is the line intercept and m is the slope here. Now if you want to map this in feature space such as m and b, we need to minimize the value of these coefficients m and b over here. Now look at this line drawn. None of these 3 points actually exist over this line. So we have to find out the difference of each of these points from this line. See here, a vertical arrow has been drawn to indicate how far it is from the line actually. So here, now this gives us the distance of each point from this line, and in order to find out this energy function, we will sum up all of these distances. This is meant by least square. Now here we are trying to find a line that gives us minimum difference of this distance. Okay, so we will be getting, we have this equation, E is equals to summation I is equals to 1 to n, those many data points we have, yi minus x minus mxi minus b whole square we are taking here. Then this can be solved by the system of linear equations, and taking derivation to this equation we get these values. Normalizing the values, we have this equation as xb is equals to 1. This is given as by least square solution. The objective here is to have the minimum distance. Now I have taken here a horizontal, a diagonal line. Now if I try to map this using some other line, I'm sure that we'll be getting maximum distance variation of the points to the line here we are trying to map. So you have to first find out the direction that is most suitable here, that will minimize the distance of each data point to the line. Now we have got some problem with this least square, as least square method fails completely for fitting the vertical lines. For fitting vertical lines, this particular least square method, this gives you falsy or error prone values here. And also this method is not a rotation invariant. Then what we need to do, we can go for total least square. Now the change here is to take the total least square method of all of the points that we have here, and the objective is to minimize the sum of squared perpendicular distances. By taking unit normal as n is equals to a comma b, we can apply there, and we have this equation, you can see, by taking the derivative of this. Now here we will be taking the second derivative and applying. Now the n value, magnitude of n square, gives you value of a, and here we have eigenvector of ut into t, that is associated with the smallest eigenvalue, that is least square solution of homogeneous linear system. Applying total least square of the second movement here, we get the equation as this. We are getting the equation as this. And now see here, this is the line that is best fitted to all of the data points here. Now look here, we have, now the difference between the least square and total least square is we are trying to take here the mean of x and y values. All of the data points, we are taking a mean of all of the data points, and we are taking x bar and y bar as the coordinate value of that mean. So always if we take first data point as x1, we try to subtract it to the mean to get the value from on to this line that represents the data points. Okay, similarly here we have y mean value evaluated. Now least square as likelihood maximization. This least square method plays an important role as it maximizes the likelihood estimation here. We can have a generative model. Line points are corrupted by Gaussian noise. See here we are assuming a model that is generated, and here we have a line, but these points are corrupted by Gaussian noise. Due to some noise, a type of Gaussian noise, these data points are corrupted. That is, they move away from the line here in the perpendicular direction to the line. Let us say this Gaussian noise term as E here. So we are just introducing this Gaussian noise into the equation, which is given by this xy is equals to uv, that is the point over the line, plus e into ab. This ab is the normal direction here. We can say the line equation is given by ax plus by is equals to d here. Now the likelihood of the points given line parameter a, b and d is given by the equation. Now this is the likelihood we are taking. Okay, that is the probability of x, the points x given line parameter as a, b and d. So here we will be applying the Gaussian equation again, which is exponential to axi plus byi minus d whole square upon 2 sigma square. And taking log likelihood of this value, we'll be getting this equation here. Now we'll see least square is robustness to noise. Least square fit to the red points. See here, these are the red points. Here we have a blue line drawn, and these red points, they lie exactly over the line. So this least square fits all of the red points here. If we try to draw another line and try to fit our data points, then look what we are getting here. Few number of data points that will be mapped over the line, and rest of the data points, and this cannot be mapped as we have changed the direction of the line. And also we have here an isolated point. So the problem is squared error heavily penalizes outliers. Now the effect of outlier is eliminated by just choosing the right scale here. By just choosing appropriate scaling value, we can minimize the effect of outlier elimination. If we choose the scaling parameter as too small, then we are going to end up with this problem. We are going to face this problem, and very few points will be fitted over the line, giving you poor estimation. If we select too large parameter, then again we'll be facing such kind of problem. So we need to cleverly select the scaling parameter. Now let us look at the other method, that is RANSAC. RANSAC stands for Random Sampling Consensus. It is a very general framework for model fitting in presence of outliers, as it can deal with few outliers. But what if we have many outliers? Now see here, choose a small set. Here this is the actual mechanism which is implemented using RANSAC algorithm. So choose a small subset of choose a small subset of data points which are uniform. At random you will be selecting this, then try to fit a model to that subset of points. Find all remaining points that are close to the model and reject the rest as outliers. Do this many times and choose the best model. So here we will be dealing at initially we will be selecting only a few set of data points we will be selecting. Then we'll be applying a model over the selected data points, and we will try to map the remaining data points which are very close to this model. Okay, and we will reject all those points that are far away from this, terming them as outliers. And this is an iterative process. We'll do it a couple of times to choose the best model. So here are the steps that we are actually doing here in RANSAC algorithm. For line fitting, here we have a loop repeat n times. That means this loop will be iterated n times. N can be any number of times here. The first step is draw S points uniformly at random. Pick up S number of points randomly. Okay, randomly you have to pick up those S points that are uniform, that are similar. Okay, then fit the line to these S points. The model selected here is a line, so we are trying to fit a line to these S points that we have selected initially. Then find inliers to this line among the remaining points. Among all of the remaining points, we try to map these points closest to the lines, and then we will and that is the points whose distance from the line is less than a threshold value we are keeping for inliers and outliers to determine the points that will be classified as inliers and that will be classified as outliers based on the distance they have to the line. Okay, if they are having lot of distances, the distance is more, then we will not select those such points, as it will lead us to some erroneous fitting. Now, if there are D or more inliers, accept the line and refit using all inliers. So, when we try to map the remaining points to this line, which are close to the line, then ultimately, when we recompute the line and accept these more points, the points are more, and we try to accept them. Ultimately, you will be getting some another sort of line here. Okay, as the number of points are increased, some other sort of line you will be getting, and this is how we keep on doing this in order to fit all the inliers. But the points whose distance are greater than the t value we have selected will simply reject them as outliers. Now, choosing the parameter. Initial number of s points. What parameters we need to select here? The number of random points that are uniform, that we are picking up at a very initial stage. So how many number of points do we need to actually select here, actually you pick up? So typically minimum number needed to fit the model. Minimum number, either 2 line, 2 points, 3 line, 3 points. These are the minimum number of points that we try to fit to a line. Based on the model, we'll be selecting S number of points. And S number of points will be minimum at initial. The second parameter is the distance threshold, that is T. So choose T so that probability for inliers is 0.95. The probability value is 0.95. You have to select the threshold. If you select the threshold as too big, then you'll be getting less number of points as inliers. Sorry, more number of points as inliers. If you are selecting threshold as too small, less number of inliers will be there and more number of outliers. Then the next parameter that you will be choosing here is zero mean Gaussian noise with standard deviation. So the value given here is t square is equals to 3.84 sigma square. And the number of samples, so choose n so that the probability p, at least one random sample is free from outliers. That will be giving you probability of 0.99, and outlier ratio is given as E here. Now look at this table carefully. Here we have the probability taken as 1 minus 1 minus E raised to S whole raised to n, which gives you 1 minus the probability. So probability will always be subtracted from the value 1 here. Now this is the proportion of outliers E, that is the ratio of outlier E to the number of points that we are selecting. If the number of points are 2 and probability of outlier is 5%, then value here we will be getting such as 2. Then if we increase 10%, 20%, 30%, then the number of data points are also increased here. So as we move on from less number of S towards greater number of S, then these values they change. Now here is the curve that has been drawn using the values in the given table on the previous slide. Now the next parameter that we have to be careful about is consensus, that is the set size T should match expected inlier ratio. The set size D that consists of the number of data points that exactly fit to the line, it should be equal to the expected number of inlier ratio. Adaptively determining the number of samples here, an inlier ratio E is often unknown a priori. So pick worst case. For example, 50% of inlier ratio we have, and adapt if more inliers are found. Here we have an adaptive method where we determine the number of samples by picking up the worst case at the very beginning. So let us assume that the inlier ratio E is at its worst because we exactly don't know priorly what is the value of inlier ratio. So we pick the worst case as 50% of inliers we have and 50% of the data elements are outliers. So we begin with this assumption, and we keep on computing more and more number of inliers, and if we find more inliers we then accept it, adapt it, and then change the inlier ratio to 80%. This will yield the value as E value, that is inlier ratio is 0.2. That is, now inlier ratio has increased to 80% and the outlier ratio is 20%. So this is an adaptive procedure where n tends to infinity and sample count is 0 at initial. While n is greater than the sample count, we are looping in this loop here. We are repeating this number of steps in this loop. Choose a sample and count the number of inliers. While we have a condition that n is greater than the sample count, repeat. What you have to repeat? Select the sample and count the number of inliers. Then set E is equals to, E is the inlier ratio, is equals to 1 minus the number of inliers upon total number of points. Then recompute n here from E. We are recomputing n from E given the equation n is equals to log 1 minus b, that is the probability of inliers, upon log into 1 minus e raised to s. S is the number of points that we have taken initially. We have to recompute n and then increment the sample count by 1. After every iteration, this sample count will be incremented and the value for e will be changed. From the value of e, will be computing n again and again number of times here. Now here we have some pros and cons of this Ransack algorithm. Ransack algorithm is a simple and general method which is applicable to many different problems, and it often works well in practical. On the other hand, it's have to tuned up with lots of parameters, as we will be selecting parameter s, we'll be selecting distance threshold, then we'll be selecting variance, we'll be selecting ratio to inliers and probabilities. So lots of parameters need to be tuned here, and it can't always get a good initialization of the model based on the minimum number of samples. Also, this is not every time applicable that you'll get a good initialization if you have selected minimum number of samples. Sometimes too many iterations are required, and this ultimately increases the time it consumes, and it can fail for extremely low inlier ratio. We can often do better than brute force sampling. So that's all for today. See you in the next class.